This video takes a look into the mysterious oscillating reaction run in general chemistry that so amazed us as little freshmen. First, we observe the actual reaction taking place. Second, we look at the general mechanism used to describe the reaction. Last, we look at the digitized data and the rate law parameters used so the experimental oscillations match the numerical simulation. Here we go!
Check out the lyrics. Darkness, no parents.
Here comes the sun. Here comes.
Continue darkness, more darkness, get it? The opposite of light.
Here comes the sun.
Curtains drawn in the basement, middle of the night.
It seems like since it's been here.
Blacked out windows, other places that are dark. Black suit, black coffee. You get it, that's just the first verse.
This is the general mechanism we can use to describe the oscillating reaction. From our rate law parameters, it is clear to see that the second reaction proceeds at a much faster rate than the first. K1 is equal to 0.001, while K2 is equal to 0.1. That is 100 times as fast. The first reaction shows the slow buildup of the yellow iodine solution, X. Once enough X builds up, the second reaction quickly takes place and the solution turns to the blue starch complex, Y. Since Y is a reactant and a product, this is an autocatalytic reaction. The blue starch complex remains until there is no X left to continue the reaction. The cycle starts over and more solution X builds up until the second reaction proceeds again. The third reaction in the mechanism describes the end of the oscillations, which was not observed in the length of time we ran the reaction.
Here, the digitized data is shown. The graph on the left shows the reaction data for the iodine solution, and the graph on the right shows the data for the blue starch solution. The boxier plot is representative of the experimental data, while the curved plots show the numerical simulation of the reaction. The goal of our data analysis was to alter the rate law parameters A0, K1, K2, and K3 to the best of our ability until the experimental oscillations matched the numerical simulation. The best fit we obtained was A0 equals 500, K1 equals 0.001, K2 equals 0.1, and K3 equals 0.8. What do the values of these parameters really mean, though? We can see this through looking at how changing each parameter changes the fit of the data. This video shows only either an increase or decrease in a variable.
First, we change A0. This parameter represents the starting amount of reactant A from the reaction mechanism. Here, we decreased A0 from 500 to 200. It is clear to see the number of oscillations decreases, as well as the peak height. The number of oscillations is the number of times the solution changes from the yellow iodine to the blue starch color. The peak height represents the intensity of the solution color. This makes sense because if you have less starting material, less reaction will occur.
Next, we change K1 from 0.001 to 0.01. This increase in K1 results in less oscillations. Since the first reaction happens so quickly, a lot of X is produced in a short period of time. This X is used up in the second reaction. It takes longer to run out of X and force the oscillations to start over. Since the second reaction can proceed longer, more Y will be produced, making the last reaction in the mechanism get reached faster. This is why each successive peak is lower than the preceding one. The oscillations are drawing to an end more quickly.
Then we change K2 from 0.1 to 0.5. This increase in this rate constant showed more oscillations of the reaction. Also, the peaks were much smaller than their originals. This occurs because before a high concentration of X can be built up in the first reaction, the second reaction quickly occurs and consumes it. Since there is not much X to react with, it quickly runs out, forcing the cycle of reactions to start over again.
Last, we change K3 from 0.8 to 5. The result in this increase in this rate constant is the same number of oscillations, but an increase in peak height. The explanation behind this is since the third reaction is happening so quickly, Y is being removed rapidly from the system. To make up for this, reaction 2 will occur to produce more Y, but at the same time this change removes X from the system. Therefore, reaction 1 will produce more X to make up for this. This results in higher concentrations of each compound, giving the greater peak heights.
This is the abrupt end to our video. Hope you enjoyed!
Darkness!